Welcome to the first session of the Electromagnetism module at Milestone. First, I would like to just go through some module info with like notions. So whenever you see a green box, those are going to contain questions. All these milestone color boxes will be the physical laws, and then the blue boxes are going to be exercises that are going to be mentioned in this class. And I will have also some parts with purple. These are the parts which are not actually part of this module, but very interesting topics about which you can ask me anytime, email me or ask me at the session time. So let's get started with this. In this first section, we are going to go through electric charge, Coulomb's law, electric fields, and electric potentials. So let's just then discuss electric charge first. I'm not really going to go through the history of it. You probably have heard of this at school. This has a long history starting with the Greeks, a bit like the naming of what the electron means and so on. And then we really jump to the end of this history, we find ourselves to the modern description, which is governed by the QED, quantum electrodynamics, by Feynman. And of course, this is also not part of this module. You can ask me offline if you're interested. They also have this module for years in physics at Milestone, which describes quantum electrodynamics. So the sources of electric charge can be several. One of them is that the charge is coming from a particle, which we call electron. It's a negatively charged particle. And so you could ask this question that if the source of the negative charge is the electron, then there is a source of the positive charges will be the positive, right? We have all heard of the fact that there are positive charges and negative charges. So one of them comes from the electron, the other must come from the positively charged electron, right? So of course this is not true. Um, we don't find positrons around us in this world. This world is mostly made of matter, and so the positron is an antimatter particle, and we don't really see it around. So whenever we speak about positive charges and negative charges, we really mean charges relative to each other. So there's more positive than the other. So it's in that sense, it's just a relative difference between the two. All right. So the first law that we should discuss, which sounds a bit trivial, but let's just really state it, that the algebraic sum of all electric charges in a closed system is constant. So you could ask, why is that really so? And actually the answer lies a bit deeper than the question you could actually expect. So it really goes back to quantum field theories and the quantum description of nature. Essentially, the answer is in the lines that there are two kind of particles in the universe: matter kind of particles, you call it fermions, and energy-like particles, whatever that means. You could also just think about them that these are the particles responsible for interactions, which are called bosons. And for example, an example for the boson is the photon. Five examples for fermions are the proton or the electron. Interesting property of the fermions is that they cannot be created nor destroyed. So that's the source of why the algebraic sum of all electric charges in the closed system must be constant. We do some very interesting things at CERN, so you can ask me about what's happening to fermions at CERN and so on. So the consequence of this is that when you rub a rod with a fur, then some electrons will move from the fur to the rod. And so we just discussed that the algebraic sum must be constant. That means that the rub will be more negative than the fur. So then now we say that the rub is negatively charged and the fur is positively charged. So there is nothing to do with the electrons and positrons in this case. All of these are just about electrons, but we say that one of them is more negatively charged than the other, and so that's what we call negatively charged, and the less negatively charged is the positively charged. So from observations, by doing a lot of experiments, we know that two positive charges, or incidentally two negative charges, repel each other, while when you have a positive charge and a negative charge, they attract each other. You could ask why that's so. That leads far. Let's just really say that we know this from experiments. So we know that the atom is made of a nuclei and an electron cloud, and then that is positive charge and a negative charge. So positively charged clouds and negatively charged electron cloud. And we just said that positive and negative charges attract each other. So the question is, why do we as humans do not repel each other? Okay, so what is now the unit of the electric charge? So when we speak about natural units of charge, then we are going to say that it is the magnitude of the charge of the electron or the proton. These have the same magnitude, right? So one of them is positive, the other is negative, but the magnitude itself is going to be the same. And so that's what we call to be the natural unit of charge. And again, what we see from observations is that whenever we see any electric charge around us, it's going to be an integer multiply of this basic unit. And this basic unit is now, if you accumulate enough electrons, precisely 6.25 times 10 to the power of 18 electrons, is going to be what we call 1 Coulomb. So to do this statement, we have to do the Millikan experiment, and I think this is going to be one of your lab assignments at university at 1.2 to repeat the Millikan experiment and indeed see that this is a true statement. There is another source of charge, which is called the induction. So let's just go through the induction with some pictures. Let's just say that we have an uncharged metal ball, we have some insulating stand to which we put a ball, and then what we will do is that we will take this negatively charged rod. We already discussed how we did that, right? We rubbed this rod with a fur, the rod became negatively charged, and so what we do is that we get this rod closer to this metal ball, and so the negative charges on the rod will repel the electrons, which means that they will create two zones, which will create a zone which is negatively, like the right side of the ball is where the electrons will be, so there will be an electron deficiency and place where there are more electrons. So we are going to say that these are now induced charges, negatively and positively induced charges. So let's now connect our metal ball to ground and with a wire. And so this wire will lead the electrons, which are built up on the right side of the ball, and what we call the induced negative charge. And so those electrons are now flowing into ground, and we still have a closed system here where the rod is negatively charged and the ball is now positively charged. So let's just now remove the wire. That means that the ground will be negatively charged, and let's also remove now the rod. And by doing that, this positive charges on the ball will rearrange themselves, and so overall we can say that the ball has an electron deficiency, and but that's what we call to be a net positive charge, and then the ground is negatively charged. So this is another source of induction or charge, which we call induction. We should also discuss some categorizations. So we can speak about insulators. Insulators, in the case of the insulators, all of the electrons are bound to the atoms. They cannot move freely, and because of that, they do not create a current. While so some examples here are plastic, glass, or dry wood. While when we speak about conductors, then this is the situation when there are electrons which are free electrons, which means that they are not bound to the atoms and they can move relatively freely through the material, and by this they conduct currents. So examples here are metals, copper, earth, aluminum, silver. And then we are going to discuss how that actually works in details. That's called the Drude model. We are going to go to the details here in a later session. There is also something which is not part of this module, but very interesting. These are semiconductors, and so actually modern technology is kind of based on semiconductors. Um, so if you are interested, we can speak about this in section time, and if this is not really part of the module, you could kind of imagine this to be somewhere between insulators and conductors. All right, so let's now discuss the next big law that in this module, that is Coulomb's law. So let's just say that we have two charges now, Q1 and Q2. Now the notion is that if it's same charges, then they are red, and then blue is the negative charge. So if they are opposite charges, then they attract each other. So the Coulomb law says that the magnitude of the electric force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So let's just set up some stuff that we say that the distance of this between these two charges is going to be r, and now we said that there is a force acting on it, which is directly proportional to the product of the two charges, inversely proportional to the distance, which we called r, distance squared. So this is r squared. And we also include a constant factor here, so that the charges are correct, and this value of this constant will really depend on the units used. People also like to use well, okay, so first of all, in the SI units, the value of this K is around 9 times 10 to the power of 9 Newton meter squared over Coulomb squared. So we can also move to the system which people sometimes prefer, which includes the vacuum permittivity, epsilon 0. So the value of the K is the same as 1 over 4 pi epsilon 0, but again epsilon 0 is the vacuum permittivity. So this is something which you have heard of so far, but now let's upgrade this mathematically a bit. Let's say that we introduce vectors here. So let's set up a coordinate system and have a vector showing to one of the charges. So x1 is vector which is showing from the origin to the q1 charge. So that's why that's x1, and then x2 is the vector that shows that points to the q2 charge. So now let's from the vector knowledge, vector calculations, knowledge of us, let's just calculate what this r is. So what I'm going to do is that I'm going to take, going from the x2 q2 to x1 or q1, I'm going to subtract x1 minus x2 is this vector that shows from here to here. Okay, so that's why we have x1 minus x2 here. But this is not exactly the same as what we have seen earlier. Earlier we had nothing up, we had just the q1, q2 up here, and we had r squared down here. Now we have this thing cubed. So what happened here is that we upgrade it to a vector notion. So the force acting is going to be a vector. That's why I have this underscore here that's denoting the vectors. And so to have it as a vector quantity, I have to multiply with this vector. So I multiply it with this vector, but then um, this is too much of this thing. So I will also have to divide with the same vector, the absolute value of that vector. So the only thing which we introduce here is going to be a direction, right? So the x1 minus x2 divided with the absolute value of x1 minus x2 once is going to just be a direction of this direction with the size 1. And then now that we factor this out, we are left with x1 minus x2 absolute value squared, right? Because I factored out one of them. So that's now the same thing, but now we can do much more general cases. So one exercise that's good to do, and we should be doing it, is to compare the electric and the gravitational force. So let's just calculate the gravitational attraction on two electrons and compare it to the electric force on the very same two electrons. So I'm going to go to some problem-solving strategies all through the module. These are going to be general statements. It probably will help you to solve problems. So when you are having a problem with that you have to use with the Coulomb's law, then which is usually the case when they are asking you about the force exerted by a certain charge. So first of all, you should make a drawing showing the charges and set up a coordinate system that could be the uh, Cartesian coordinate system or spherical coordinate system or cylindrical coordinate system and so on. And then let's calculate the electric force on these charges. And then let's put the vectors into this notion. So let's sketch the vector, and then we can calculate that electric force by adding these vectors together. So now, it's very important that you are consistent with the units. There are several units out there. If you use SI, you should be using the SI system all along. I mentioned that you should be choosing a coordinate system according to the problem. So when you have a system which is like spherically symmetric, it makes sense to use a spherical coordinate system. Or if we have a rod, right? The rod is like a cylinder, so cylindrical coordinate system is probably more helpful than the Cartesian coordinate system. Sometimes you will get results that mathematically are the outcome of your equations, but physically make no sense. So always make sure that what you got is not completely unphysical, unrealistic. So the next thing to discuss is about the electric field, and this comes to the picture when you are asking this question. When you have two particles in empty space and they interact with each other, how do they know that the other one is there? I mean, I say no, it doesn't really mean it consciously, but how is there some information about that the other electron or the charge is there? What goes in space between the two of them to communicate this effect on each other? And so the answer to that was coming from Faraday, and he said that these charges, let's just call it Q1, will create a field which we will denote with E. It's a vector field, and so this field is now understood everywhere. And so when the other charge is interacting with this field, that's what we call the force. So the law here is that the electric force on a charged body is exerted by the electric field created by another charged body. So to define the electric field, we will be using a test charge which we call Q0. and if the test charge experiences any electrical force, then there is an electric field at that point. So let's just say that now the electric field, which is a vector, is defined by the electric force F divided by this unit charge Q0. F is a vector quantity, so when you divide it with a scalar, it still will be a vector. It's good because the electric field is a vector field. So if you look at the units, well, that's going to be the units of the force divided by the units of the charge, so that's Newton per Coulomb. And so the force, we discussed that has this vector formulation of the 1 over 4 pi 0, epsilon 0 times the charges. In this case, our charge is Q0, right? That was our test charge, multiplied with the Q1, which is the original charge, creating the electric field. And then you have this location between the two with this vector formulation. So we just said that the electric field is the division of the force with the Q0. So when I divide this thing with Q0, then the Q0 just cancels out, and we get that the electric field is the charge which creates the electric field and this location of wherever we are. So, x1 points to the charge q1, and x points to wherever we are interested in the electric field. So the electric field, as I mentioned, is a vector quantity, and its direction is radial. And so if I have a positive charge, then it's an outward pointing radial vector field. And we have a negative charge, it's an inward pointing radial electric field. So the interaction itself is done with this particle which we call the photon, and the details are again in the modern physics classes, frontiers in physics, for example. And so one interesting fact is that the fact that this interaction happens almost immediately is due to the fact that the photon is thought to be a zero mass particle. However, experimentally, we can only prove that the mass of the photon is less than 1.6 times 10 to the power of minus 47 grams. If you're interested in this experiment or these results, I'm happy to send you the paper about it. So let's discuss electric field lines now. This is just a visualization. We already discussed that when you have a positive charge, you have outward going radial electric field. When you have a negative charge, it's an inward going radial field. So when now you have two charges, which you call a dipole, then this is how the electric field lines look like. If you make these two separate, then you get back this situation and the situation from the previous slide. But as you get them closer, you will get this dipole. Field lines always point away from the charges in the positive and towards the charges for negative charges. And at each point in space, the electric field is tangent to the field lines passing through that point. So this is the field lines, and this is the electric field in it. So you have two charges which have the same sign. So let's, for example, say that you have two positive charges, then the field lines are close together where the field is strong and farther apart where it's weaker. So the density of the electric field lines is connected to the field value. So we already established that this is the formula to get the electric field, and then you have one charge creating the electric field, but then you can go on and ask, what if you have several charges creating this electric field? Well, then what you have to do is that you have to add up these charges. So I'm going to introduce Qi as the charges around. So the I is the index which is describing all these charges. All these charges are located at xi points, and so what we do is that we add up these things factorially, right? And so what we do is that we look at the first charge, we calculate this value, and then divide this thing, and then we add the next one, and this addition is coming through here with the sum here for the I. In case you don't have discrete charges that you can just sum up, but you have a continuous distribution of charges, then this sum will become an integral. So you are integrating for the charges, and so a little charge is going to be called the q, and then you calculate this value. It's good to have three categories with the three dimensions. So in case when you have a one-dimensional system, it is usual to call this one-dimensional line integral to be denoted with lambda for the charge density. That's the one-dimensional charge density. And then in one dimension, we could just go in this x direction. In the 2D case, when we have a surface integral, then this dq is understood to be a sigma, which is the charge density for the two-dimensional case, and then the a is the little value for the surface. And then you have 3D, it's usually called with a rho instead of lambda or sigma, and then this is now volume integral, so we do dv here instead of the dA or the dx earlier. That's a volume integral. So when you have a charge distribution and they are asking you about the electric field, then this is the problem solving strategy to follow. You, as we mentioned earlier, should make a drawing and indicate the direction of the field on this drawing. You should be very consistent with the units, as they can lead to serious issues after all. And remember that we are dealing now with vectors, so whenever we are adding them or subtracting them, they will be vectors too. And as I mentioned earlier, you should be taking advantages of any symmetries of the system. So when you have a continuous function, then use an integral to get the results. And if you have a discrete system, then just sum the charges up and the vectors. And in the end, you should always make sure that your answers are reasonable. Let's just go into a bit what electromagnetism means in the real life. So if you could think about this question of why my mug is on the table, right? So why is the mug not falling through the table? It has to be doing with the forces, right? Or what is the reason why water is such a good solvent? That actually has to do with the dipole system of the water. And if you go to like more complicated chemicals, which can include a metal in between them, why is that so? What is really the reason here? Or you can speak about, is friction a fundamental force? What is really friction from mechanics? So I'm not going to answer these questions now. We can discuss them during the section time. The next thing to discuss is about the electric potential. So let us define the charge and the field to be as a system. And if the charges are free to move, then it will do so in response to an electric force, and therefore the electric field will be doing work on the charge. So it is important to go through these thoughts again, because that's the basics of why electric potential exists. This work is internal to the system, and so we define work to be the force times the displacement. And so work is a scalar quantity, while the force and the displacement are vector quantities. So what we do is that we are multiplying these two vectors as a scalar product. So what was the force? In here is the electric force, And so what was the way to calculate that? That was the electric field times the charge. So the electric field is a vector value, charge is a scalar. So we will be discussing that this internal work done in the system is equal to the negative of the change in the potential energy of the system. So the potential energy, a little potential energy done in the system, where is going to be the same as the work, just with the opposite sign. So we will be doing minus q times electric field times the displacement. And if we are interested in the full potential energy of the system, not just a little piece, which we denoted with u, we will have to integrate this the u to get the delta u. So the q is independent of where we are, the electric field and the displacement is dependent. So the q can be taken out from the integral, as the minus side can be. So now we are going to do a line integral of the electric field from point A to B, and so this drawing is just a general drawing of what we mean on the line integral, and we will be going through this in session time as well. And also I have videos about line integrals in the videos about what are the math needed for physics. So let's just again explain this picture. The blue is that kind of field that you have around. So that's the electric field in this case. So Fr means that whatever field is here depends on where you are. So in our case, this is the electric field, and the electric field is, as you know, created by one charge, is going to be a radial volume. And then let's say that we move on this red path from this point A to this point B. So what we do is that we take little pieces in this path, and that those small paths are going to be the R, what we call, which equals the R, and what we call the S here. And so what we do is that we look at the value of this electric field in our specific case, or Fr in the general case, at the middle of this line element, and we will, these are both vectors, right? So we will be doing a scalar product, an inner product of these two, and then we will add up these small pieces to get the whole thing. And then we say that this dr or the ds in this case goes to smaller and smaller and smaller values, then the summation will become an integral. And this is what we call a line integral. So let's just think about if we do this integration on different paths. You see one path like this, one path like this, one very complicated path like this. So a force is going to be called a conservative force if the line integral doesn't depend on the path taken. So if the line integral of this upper curve, the middle curve, and the bottom curve is the same, and the force on which we are doing this line integral is a conservative force. So we were discussing potential energy so far, and when we divide this potential energy by the charge, it gives us a physical quantity which depends only on the source charge distribution, and it has a value at every point in an electric field. So this quantity is called the electric potential. So again, we derive the electric potential using the potential energy, and this electric potential sometimes is just called potential, and we denote it with the letter V. So U was the potential energy, and when we divide it with the Q, we get the potential V. Potential itself is less physical, but what is really physical is the potential difference between 2 points, which is denoted A and B in this electric field. So we will be defining this as the change in the electrical potential energy of the system when a charge Q is moved between 2 points. So the left here we already discussed that delta V is the same as delta U divided with Q, and we define the U to be minus Q times this line integral. So when I divide with the Q, I'm just going to keep that it is minus the line integral of the electric field between points A and B. That's the potential. So this potential is the measure of the potential energy per unit charge. So the SI unit of both the electric potential and the potential difference is joules per coulomb, which is defined to be a volt. So 1 volt is 1 joule per coulomb. You can also ask the question in the other direction. So now we said that we can get the potential from doing a line integral of the electric field. What if you are interested in the electric field? So you could also just think about it that this is the inverse of doing the integration. So what is the inverse of an integration? But that's going to be the answer. But before doing that, I would like to just look at the situation that we are just doing a very little potential and it's very little displacement. So not the full one, so not doing the integral, but just doing an infinitesimal one. So that is dv is going to be then the same as the minus E times the S, and I'm interested in the E. So if this was just normal numbers or algebraic values, if you're interested in E, what you would do is that you divide with the ds. And so we have to make it. So first of all, we would have to divide the ds, which is a vector, and we should not do that. But we should say that okay, we are just looking at this at the x dimension, let's say. So then the s is going to be the x, and the e will become ex, which is now not a vector anymore, and we are happily dividing with that. And so minus dv dx is what we is the value of the electric field. And so this with the limit goes into a derivative, and then you do this in the all dimensions. This will introduce us the gradient. So when you do a derivation in each dimension, is called this nabla operator, and so minus nabla scalar multiplied with the potential, which is called the minus gradient of the potential, is going to be the electric field. I have another video about what the nabla is, and we can also again discuss it later. So if you just want to do this in one dimension, not in all of them in one go, then it just means that the electric field is the partial derivative of the potential by x. The electric field in the y direction is the partial derivative of the potential in y, and the ez is the partial derivative by z. So again, problem solving strategy starts with making a drawing and then setting up a coordinate system. You should always indicate where is the null point, and then find the potential due to the collection of the point charges, carry out the integration, use the symmetries if there are any. That makes life much easier. And if the electric field is given, then use the line integral and be always consistent with the units. Whenever you have the solution, you should sketch it and make sure that your results are physical. There is one more thing I want to discuss. This is the method of image charges. So let's just consider that you have a grounded conducting plane, this thing, and a set of charges. Let's just call that Q. So the electric field created by this charge induced by this plane is the same as if you were to remove this plane and mirror it. That's why it's called the method of image charges. That's its image for that view. But the difference is that that's going to be, that charge is going to be the same, but with the negative side. So it's the opposite side. So the electric field created on the left is exactly the same as the electric field created on the right. It's a very handy method to figure out electric fields when you have plane and and the charge. That's all for today, and next time we will be discussing Gauss's law and its applications. If you like this video, don't forget to like it and ask me questions in the comment section.